The second speaker is Mathieu Duprez from AEM Company. Mathieu is the head of the ATE core technology team of AEM Company in France and Singapore since beginning of 2020. Mathieu has more than 30 years experience in R&D AT industry. After receiving the master's degree, he spent first 20 years of his career in Schlumberger and Picast Credence design groups as a design engineer and project manager for conceiving state-of-the-art instruments and system architecture from DC to multi-land BPS high-speed communication system. Also, in 2008, Mathieu has been founded new test company, test company, to provide semiconductor industry a cost-effective, comprehensive, scalable test platform solution for SoC devices and upcoming test technology. Let's welcome Mathieu.
Thank you very much for your introduction, Wendy. Good morning, good afternoon, and good evening and good night for everybody all over the world. So the DPS requirement for semiconductor testing is the sum of many different configurations in terms of voltage, current that goes from a few milliamps to 100 of amps for some market, and each of those DPS needs to be able to measure current, to have clamp capability and very good behavior, dynamic behavior, especially high DI over DT. Today, I'm going to present the way at AEM we see the future of device power supply and what solution we propose, lowering test of cost for our customer and improving our return on investment and cost model at AEM. So I will first go through the market and test requirements depending on the device you want to test. Then I will detail some solution we bring and what key design manufacturing challenges we had to solve. And I will go to a short conclusion. So here I'm presenting the key duct power supply requirement, which is driven by the duct process, the duct feature, and test scalability. At AEM, we categorized the DPS requirement in mainly 4 types of needs and solutions. On the most left, we find the linear, some part of automotive devices, high reliability processes, and a little bit of RF. Those requirements correspond to middle or high voltage. This is going up to 80 volts. This can be also called VI source, which somehow is a DPS, is a device power supply. The second category is represented by sensor requirement. We have here devices with 4 to 8 different power supply for a total power, which is most of the time below 1 or 2 watts. And so the number of power supply might be a showstopper for large parallelism configuration, especially in a wafer sort. Then we find the microcontroller SoC market. The need, those devices to be tested need 2 or 3 main power supply, like the processor core, the I/O, or DDR3, DDR4 memory bank. Each of those PSU might require 1 to 5 amp. in addition to those middle range PSU, they might also require a few small PSU in the 20, 50 milliamp range that are used for PLL, internal references, and sometimes some analog features. All of them obviously require small noise requirement. And the latest category on the right is the one that forces AT suppliers to provide new solution almost every year. This category contains the high-end processor, graphical processor, and datacom processor. In functional mode, I mean in your computer, they require 50 to 100 watt. At 1 volt, this is 100 amp. In test modes, it can go easily up to 500 watt under a little bit less than 1 volt. And sometimes we are switching 20 to 80% current in less than 50 nanoseconds. So this drives a very specific requirement for the high-end processing, GPU and datacom. Parallelism for those devices is commonly 1 or 2 devices driving 2 very high current supply needs and another set of 2 to 6 middle range PSU for IOs and PLLs. So this is a requirement. AEM is trying to fulfill the requirement for the sensor, microcontroller, and processor. So here I'm showing, I would say, what is available on the market through the AT provider and also on-the-shelf instrumentation. So you will find some DPS instrument running 32 channel most of the time, 1 amp, and you can find different ganging configuration offering 4 amp, 8 amp channel. You also find sometimes called VI source, but they are DPS. So instrument with over 100 channel running 3264 milliamp. Sometimes you can gang them. And you also have available on the market some DPS instrument or dedicated external amplifiers that can be ganged together. They offer 32 to 40 amp, and ganging them together, you will fulfill the requirement for 100 amp, 200 amp needed for high-end processor. So sensor market will be covered by high channel count, low current. Microcontroller are covered by middle range DPSs and high channel count board, while high-end processors are covered by high current amplifier and sometimes middle range amplifier and low current range boards. So we end up with different system configuration in test floor, each of them being dedicated to a specific device category. There is no flexibility, and a given platform cannot cover the full device spectrum. In contrario to the digital instrument offer, which is now available to cover a very large part of the device requirement. But now the platforms are still dedicated due to the DPS architecture. So at AEM, the DPS offer now resumes in a single instrument, which is 128 channel, 1 amp per channel. We can configure the instrument with almost any ganging configuration. We can also gang the instrument together. Up to 4 instruments can be ganged together, reaching 512 amp. And so as we can see with this type of solution, the instrument covers the need for the low voltage market, meaning from -2 to +6 or +7 volts. We can have a mix of low current or middle current DPS covering the microcontroller and SoC market. We can have large channel count for the SoC, for the sensor market, offering large parallelism capability, and also very high current capability with middle current capability for high-end market. So this instrument and the platform can now be used for many applications, allowing a better system usage. You only have one system covering all the different digital market. So as AT provider, reducing the cost of the DPS is very important. This is important for our customer. This is important for us to improve our margin and reduce our R&D cost. As a matter of fact, to the exception of the very high current channel, the DPS cost is often considered by the customer as being part of the system structure. When finding solution for high current channels, the specification and especially the dynamic performance of the instrument is truly part of the decision criteria. But for low and middle speed device, a lot of customers are taking into account the price of digital channel. How many channels do I have? 5, 12, 1024, 256. But they do not take into account the price of the DPS. And so for AT provider and user, this makes system pricing comparison complicated and unfair. Having a single instrument covering wider spectrum allows cost unification. We talk not now about cost per amp or cost per channel, whatever application the instrument is being used. So now that the requirement and the specific, so we work with the sales and marketing to see what is the market expectation and our AEM expectation as well. And so we end up with a single instrument covering, as we've seen, all the SoC sensor and high-end processing market. We are trying to reduce the cost of the instrument by improved integration, a unique amplifier covering all requirements, and a design for very high reliability. The instrument provides with the key features that are used in all this market, meaning measure current, gain capability. We also need to provide programmable slew rate, power supply rejection ratio capabilities through test noise injection. So having the sales and marketing requirements, the engineering can start working having the constraint in mind. So the key constraints are low cost, high reliability, and at spec. We've been working on different DPSI C-cell, evaluating some device through a mock-up and a proof of concept, trying to find the best cost specification. Then the instrument is divided into multiple modules in order to have a good compromise from cost, inventory, and manufacturability. So we find out at engineering that we could reach up to more than 250 amp per instrument. This has been reduced and divided by 2 just to ensure a high reliability and a low theta GC, junction temperature on the at the amplifier. Our systems are air cooled, and so we need to ensure a very good we need to ensure that the amplifier is properly cooled. So we have retained 128 channel as being the optimum number, and then we try to see what is the best configuration for the instrument in terms of modularity. And we end up with this solution. We have a high technology module that takes care of high-speed communication, computing. It can also be reused on some other application. This module is used to perform the instrument configuration, measurement history, and ganging mode. We have on the other side the heart of the instrument. This is a 16 amp module. It has 16 channels of 1 amp that can be ganged together. This is a high density analog module. This includes preamplifier, amplifier, and measurement capability. And then we have a low cost, what we call front-end module that supports up to 4 16 amp module. It is used to bring the power to the dot through the pogo block. So with this configuration, we can have 128 channel or even 64 channel for engineering configuration. This provides us with a low inventory value, and all those modules can be interchanged in the field, on the field. So one of the key challenge is the output amplifier, power yield, and the cooling of this amplifier. So the best yield is obviously PWM. However, this is not the best AC. This will not provide with the best AC response. Best AC specification is provided with linear amplification. With a full linear design, a high-end processor core PSU at 0.8 volt, we will reach only 8% of power yield at the instrument. This means that if we have 100 amp, 100 watt at the dot, the instrument need to get 1.2 kW. So this is about 8% yield. And the issue is this is also 800 watts that has to be dissipated and air cooled at the instrument level. So this design is not affordable. So we went through a mixed PWM LDO design, low dropout amplifier, that significantly improves those figures. We have an output amplifier with 2 volt that provide us with 2 volt margin at the amplifier per supply. And so now with this, we end up with close to 25% yield, meaning that we can have 100 watt at the dot. The instrument itself needs to dissipate 300 watt, which is largely doable using air-cooled mechanism. However, the cooling of the amplifier remains a challenge. So we've been simulating a different combination and tested them. So different heat transfer. So in one case, we have the dot or the amplifier underneath the heatsink and some decoupling and glue under the PCB. In another case, this is a reversed solution. And the third configuration which was tested is the heatsink covering the full printed circuit board. Inside the printed circuit board, we have dedicated heat transfer layers. And so we've been solving the theta GC equation by first simulation, different number of many different configurations with thermal via, type of thermal pad using via fill. And after selecting 2 solutions, we've been through a different mock-up and selected this configuration in which we have the best transfer between the heatsink and the thermal via. So we've tested a full instrument running 128 amp in the worst condition, meaning driving 0.8 amp, and trying to verify the DPS amplifier junction temperature. In those conditions, we have a junction temperature close to 85 degrees, which was simulated 90, and the device supports 100 C junction temperature. So through the simulation and the experiment, we now have a design that ensures a high reliability and in the future for this instrument. Another challenge is the noise injection capability. So for sensor and also for high current power supply, the customer would like to be able to verify that the DUT works properly when there is noise on its power supply. So we had different possible configuration for the noise injection. First, we first decided to have two noise sources within the design that can be sent to the different amplifier through a different injection point, which can be the sense plus, the force plus, or the sense minus. And so we made some experiments with this, and we find out that the best configuration in terms of price, in terms of capability, was more to modify the amplifier design to add AWG capability instead of using static voltage reference, improve the regulation stage and amplifier stage. So by doing this, we end up with a design that allows to inject noise up to 100K. So obviously you can see on the left side, so the first result, injecting noise at 1K on the left and then 100K, where we had more than 10 dB loss on the design. And so there was no way to improve the amplifier bandwidth. So what was done, because we have enough margin, is that all modules are properly characterized upon frequency, decoupling, and gang. So we provide with a flat response or almost flat response depending on the noise level, noise frequency. One of the key challenges also is to ensure a correct and a very good parallel efficiency. So this is a key parameter for a test system. Even though we may think, okay, a DPS is something that goes slowly, so we can afford to have a slow processor driving the DPS and doing the configuration. This assumption is false because configuring the instrument, doing the V-Connect sequence can take hundreds of milliseconds if not done properly. So at AEM, we invested a lot into parallel processing into FPGA, high complex state machine. And in fact, the processor, which is an FPGA on the backend module, will take care of the V-Connect sequence, the power up of the DPS. It will take care of the gang configuration. And this processor is duplicated as many times as we, is duplicated 128 times, such that we ensure very high parallelism efficiency. Again, the latest, so one of the latest challenge was the gang capability. So we start up with the ideal design where all channels have gang in and gang out IOs, and we have a large cross point and we start to play with it. So it works fine for 1, 2, 4, 10 amps. When we reach high current configuration, we hit some bandwidth issue and some feedback issue. And so after qualifying the amplifier response and the feedback pass response, we end up with a design, what we consider being the best compromise. So every cluster of 4 channels have a gang out I/O. We have local 8x8 cross point, with a bandwidth up to 500 megahertz. And from ganging 2 channels up to 256, 512 channel, we only have 2 levels of cross point. And this ensures us a very high accuracy setting point, a high current measurement capability, as well as good DI over DT response time. So those were the key challenge we had to solve during the R&D phase. So now we have an instrument that covers those markets. I mean, the sensor, high parallelism, little current, microcontroller, middle current, middle range of parallelism, and 1 or 2 devices in parallel, but very high current. This instrument is released and start to be released to customer. And so next step would be to use the same infrastructure, meaning same backend module and front end, and simply modify the analog module to provide with linear capability. With a linear and RF and high voltage capability. So as a summary, we think that to properly answer our customer requirement for device power supply, the solution is to provide a single power supply that is scalable, flexible, gangable, from high power to a large number of tester channels. The instrument maintains very good dynamic performance in all configurations. And the FPGA flexibility ensures that we have a high yield in high parallelism configuration. So, yeah. So this is the end of my presentation. Thank you for your attention, and I'm happy to answer any question if there are some questions.
Any question? Thank you, Mathieu. Share about your very creative design, and also share the very detailed verification for those of the design. Thank you. And
thank you.
We have 2 minutes. Please, everyone have any question? They have one question. Let me see. The question is first question. Sorry, the name might be the question is any qualification numbers on dynamic performance?
Yes. So here we spend a large number of time qualifying and improving the amplifier for high current dynamic performance. So this is the configuration is the following. So this is moving from 20% up to 80% within less than 10 nanoseconds. And here we are considering 256 amp, meaning 2 instruments in parallel. And what we see under our recommended decoupling condition is less than 50 millivolt voltage drop, and recovery time happens within 30 nanoseconds.
Yeah, thank you, Mathieu. It's very detailed answer. If you have any question, you can come. Sorry, yeah. Wow, many questions coming. Yeah,
Okay.
yeah. Another
So
question is,
I
yeah,
will go very quickly through finishing the answer to Kumar. Yes, we have some bulk capacitor on the load board required for very high switching current. And
yeah.
okay, there was one question about COVID, but it has disappeared.
Okay, thank you, Matthew.
So thank you very much for your attention.
Thank you.
And last but not least, I want to thank our sponsors again who made today possible. Test Tooling Solutions Group is our premier sponsor. JDT Technology is our honored sponsor. Our distinguished sponsors are Nidec SVTCL, Smiths Interconnect, TSC, and Feldman Engineering. Please visit their listings on the TestConX website, reach out to their staff with any questions. They're there for you, and they're happy to engage with you in any way you want to engage. And also, I'd like to thank our media partners as Silicon Semiconductor China from ACT and EE Times China, who's also producing their Double Summits conference coming up next month. So you can click onto these on the website for additional information. And then once again, an extra special thank you to Test Tooling Solutions Group, who has a wide range of solutions, and they would like to hear from you. So please take a moment and thank them again. And would like to thank everybody else, everybody on for attending. Tomorrow's session 3 will be on high frequency and 5G and high speed data. It will start at 9 a.m. Shanghai time. A reminder, the Zoom links are different every day, so you'll need to use Thursday's Zoom link, or if you're on Bilibili, the same link will work tomorrow. So we look forward to having everybody join us there. And with that, I would like to wish everybody a great rest of their day, and I look forward to meeting with everybody tomorrow. So thank you.